So, our first speaker, Daniel, software engineer, founder of the Rock JVM, an online platform teaching Scala, big data, functional programming to over 100,000 of students worldwide, including engineers at top companies like Adobe, Google, and Microsoft. His YouTube channel have over 25,000 subscribers and 1.5 million views. He also taught more than 50,000 kids how to code. So a warm applause for Daniel. Welcome, Daniel.
Thank you. Thank you very much.
Stage is yours. We're just going to hook up the laptop, which is usually the most tricky part of this.
Should we go?
Should work.
First try. You know that feeling when the code compiles on the first try? You wrote 1,000 lines of code and it just hit run and just it works? That. Okay. Hey everyone, thank you so much for coming to this conference. It's so good to see everyone in such a packed room. I am very happy to talk about effect systems in Scala. Now first, I wanted to ask, how many of you have written or are writing Scala professionally? All right, so this is the Scala side and this is the non-Scala side. Okay. So for those of you who are not Scala developers, the funky Scala syntax I'm going to explain. Pretty much everything else I'm pretty sure that you can kind of map around, because if you're not writing Scala, you're writing some other beast of a functional language like Haskell or whatever. So I'm pretty sure you can catch up on the syntactic things. This is a technical presentation on effect systems. From the Scala people, how many of you have heard about Rock the JVM? Can you raise your hands? All right, so pretty much the same people. Thank you so much for following my work and for joining me in this presentation. So we are at a functional programming conference, so we absolutely love functional programming. We like to think that our code is much more productive, that we are more productive while writing code, because our code is far easier to read and understand, which makes it easier to transfer to other people and for us to collaborate. And two very important principles that allow the code to be that is referential transparency and local reasoning. Oh, before, I forgot to ask a question. How many of you are mid-senior or above level? Can you raise your hands? Good. Okay, so I'm going to skip basics. You're probably going to map up the essentials. So referential transparency allows us to replace expressions with whatever the value of that expression is. So if I write something like this, it's just a basic function that adds two numbers. All of those values below, like the combine and 2 plus 3 and 5, all of those are replaceable with one another. That's what local referential transparency means. And this is the principle behind immutable functional programming, in the sense that it allows code to be easily readable, understandable, and also, I didn't mention on the slide, easily refactorable, because due to the fact that those expressions are interchangeable, you can swap code around without changing its meaning or losing trust in the code. So all of these are replaceable with one another. But we have kind of like a devil in the equation, which is side effects. And we like to think that side effects are bad because they can either break our control flow, or changing variables lose the meaning of immutability, so it makes it harder to track our code or refactor things. And not to mention concurrency and synchronization, that is completely going to blow our code out of the water. But side effects, bad as they are inevitable and they're necessary, because we need to be able to interact with the software. The computer is not just a computer that you press a single button and spews a single value and then everything is fine and good. We need to be able to interact with our software. And we need to make things happen in the real world. That's why we are software developers. We are processing things in the real world. So all of these examples that you see here on the right-hand side, they're examples of side effects, like printing things or changing a variable or logging things or potential interruption of code flow. These things break referential transparency because the expressions that do something in the real world cannot be replaced with the value of that expression, which in Scala we have that little thing, the parenthesis that's called unit. It doesn't do anything. It's like a void in other languages. So we cannot really change the print line with the void because besides the void, it actually does something in the real world. That completely breaks the mental model. So why not encapsulate code that is potentially side effectful as a value? So in this way, we would keep referential transparency and we would continue to love functional programming with the potential of using side effects. And effects are these data structures that can potentially manage possibly side effecting computations as a value. So you can compose them, pass them around, return them as results. So here on this screen, you can see the criterion for deciding whether a data structure is an effect or not. So I'm going to introduce the concept of an effect. First of all, the type of that data structure should describe the kind of computation that will be performed. The type of the value contained within should also be part of the type signature. And very importantly, if the computation of that data structure produces side effects, those side effects must be deferred. In other words, the construction of the data structure and the production of side effects, or the execution of the code that is wrapped inside, should be separate. And I'm going to give some examples of things that are effects and things that are not. For example, the option or the maybe type in Haskell. This is an option. An option is used to wrap something that could potentially be absent or not exist. So we create a function that does like a million things and can potentially return something, or it may not return anything or return null. And we wrap those in an option because it allows us to do functional programming with maps and flat maps and get or else and things like that, the likes of which we functional programmers like to do. Is this thing an effect? Well, we can run through the criterion. And yes, this describes a potentially absent value. So this is the description of the computation that will be performed. The type of the value is contained within, so the value that might be there or not. And in case of side effects, the description and the execution of this data structure are separate. And in this case, we don't really need to perform any side effects to build an option. In this case, we don't really require side effects, so we kind of cross the question off the list, or we can say simply yes. So option is an effect. And in practice, it's used, for example, for testing or to replace a Uber effect that I'm going to describe later. I'm going to describe another kind of computation, which is a future. In Scala, a future is a deferred computation in which you can suspend a computation on a thread and run it on a thread, and the value that will be returned later. So you can have all these async callbacks like on complete and whatever. So is this future an effect or not? This is another example. The first question, the type should describe the kind of computation, and it is descriptive. It describes a value that will be returned later, and the computation will be performed on a separate thread. The type description should contain the value of that computation, and yes, it's a future A, so it's usually generic. And in case of side effects, the description and execution of this thing should be separate, and in this case, it's not. Because when you create a future, it automatically sends that lambda, so you can see the curly brace thing, that's a lambda for the non-Scala developers, that is scheduled to run on a thread immediately. So it's directly started the computation. So the execution and the description of the data structure are not separate. In this case, future is not an effect. Let me go to another data structure that I called my effect. And this thing is just a class that wraps a lambda that takes no arguments and returns a single value, and with some pretty interesting transformers like map and flat map. We all know and love these transformers. Is this thing an effect? Well, we can run through the same questions, and in this case, the type does describe the kind of computation because due to the fact that it wraps an arbitrary lambda, this wraps an arbitrary computation that can perform side effects. And it's an arbitrary computation that does return a value if it's successful. And the type description does contain the value of the computation, it's the A inside. And in case of side effects, the description and the execution of the effect are separate. What do you think? Are they separate or not? How many of you think that these are separate? Yes, that's the correct answer. So nothing gets executed until that lambda is being invoked. So the description and the execution of the computation are separate. We call this an effect. Now, this my effect thing is particularly powerful because due to the fact that I'm wrapping a lambda, this can perform pretty much anything. This can start an AI that can rule the world and destroy us all. But, this is just the description of an AI that can destroy us all, right? You need to actually invoke the unsafe run in order for the AI to actually kill us all. So this is the introduction of a super effect, because this is a powerful abstraction that can describe pretty much anything that can be performed. It obeys monadic laws. I added the map and flat map there for a reason. So if you start to prove the monadic laws, this is a monad. It is referentially transparent because you can pass it around like a value and not change the meaning of your code. It can be changed, passed around, and it can be enhanced with other kinds of transformers like error handlers and parallel computations and tupling and all sorts of data massaging. It can be scheduled to run on a thread, which opens the door to powerful concurrency primitives. And I'm going to start describing these kind of super effects or uber effects. And in this presentation, I'm going to talk about the two most popular effect systems in the Scala ecosystem. One is called Cat's Effect, one is called ZIO. There's a third one that's popping up, it's called Kio. This is in development and it's going to turn 1.0 in a couple of months. But I'm going to describe the main principles of uber effects by talking about one of the effect systems. And without any loss of generality, I'm going to talk about Cat's Effect. With ZIO and Kio, you're going to see later that the concepts that I'm going to talk about are going to be transferable to the others. So once you learn one effect system, you can potentially learn all the effect systems at once with a bit of changing, with a bit of, let's say, different kind of phrasing of effect systems, with pros and cons in terms of architecture. And by the end, you'll understand, hopefully, why these effect systems are useful, and also some advice on whether you should use them at all. So this is what the talk of to effect or not to effect is all about. So without loss of generality, I'm going to spend a bit more time in the presentation talking about Cat's Effect, and then the concepts are going to be transferable to the others as well. So the Cat's Effect IO is a direct representation of the Haskell IO monad, and this is a direct enhancement of the my effect that you saw earlier. So this is basically a data structure. An IO is a data structure that can abstract away any sort of computation. And Cat's Effect enhanced the constructors of these IOs with various kind of smart constructors. You see IO.pure, IO.delay. There are many different constructors that can build arbitrary effects. And you have monadic transformers like map and flat map. And in Scala, we have four comprehensions, which are syntactic sugar for map and flat map chains. So if you look at a for comprehension, you see this program, and it's pretty imperative in the style that you see the code lying around. So it just reads a line from the console, reads another line from the console, and then it combines those together by printing them out. That, for comprehension, is a value that you can pass around. That program doesn't execute the moment that you define it. It only executes when you call a run on it. So this is a super effect because it can model any sort of computation, and it embodies this idea of a program as a value that you can compose and pass around. Now, Cat's Effect being a full-blown library, it enhances this IO data structure with a variety of transformers. For example, for error handling. This is an example of IO delay with throwing a runtime exception, which normally would interrupt the flow of the program. But because I'm wrapping that in IO, that's just the description of a program that will fail if you run it. It doesn't fail the moment that you describe it. And handle error with is another IO that, if executed, will run the first, and if it catches the exception, it will perform another effect. And you can chain these around, and you can design business logic in terms of these values that you can enhance and transform. You can also parallelize effects and run effects independently, so you can use the parallelism of the system. Here, in this case, you have a tuple of two IOs, and you have this constructor called par_map_n, and then you can pass a lambda that combines these the values together when the effects are done executing. What's very interesting about Cat's Effect is that this particular data structure is ripe for concurrency because due to the fact that you can pass programs as values, concurrency is made far easier. Now, hands up if everything that I've talked about so far makes sense. Right, I love that. So, Cat's Effect introduced a while back this sort of idea that you can execute effects on other data structures that describe a logical thread without the necessity of loading, unloading, and context switching of platform threads, which are very heavy. And as you know, context switching is very penalizing for performance, which is why Cat's effect has this concept of a light thread, also known as a fiber, and you can call start and join on a computation, and this is another effect that you can manage at a low level from the point of view of thread manipulation or concurrency. So this opens the door to a whole array of computer science problems that you can solve far more easily with effects with this idea of programs as values. One very important idea is the idea of semantic blocking. Semantic blocking means that a program, when executed, will block, but it will not block a running thread. It will only logically block a logical fiber or a light thread, but the platform thread is free to execute or run other effects that might be pending on its queue. So Cat's effect has this work-stealing fork join pool that picks up effects from the queue and processes them, and whenever an effect has semantically blocked, it will be just descheduled, and it will be blocked, and it will be scheduled to run at a later time. From the point of view of us as programmers, we still get blocking effects, but we still have the fast performance because no JVM threads or no platform threads are actually being blocked. We also have the concept of cancellation because effect chains can be interrupted without the very heavy thread.interrupt calls, which, as you know from either the JVM world or other VMs, or even if you're writing native code, interrupting threads is very penalizing. We also have, because we have this concept of a fiber, we have timeouts, we have retries, so you can do all sorts of logic based on this idea. Obviously, we also have error handling and the concept of racing, which cancels the losing effects naturally or without us having to intervene in any way, all with the same assumptions. So these IOs are functional programming composable data structure that you can transform as you like. For example, let me take a look at this piece of code, which is a race. So we have two effects. One is called meaning of life. One is called favorite language. These are the two things that we work with most of the time. And we do an io.race between these two. One sleeps for 1 second, one sleeps for 2 seconds. It's obvious which one will win or will produce the first result. And we can process the IO that is obtained at the end of the computation with a flat map in case we get a left or in case we get a right, meaning either of these two things has one, we can run other effects accordingly. The only important call is the io.race because this cancels the losing IO. So if we have the favorite language that sleeps for 2 seconds, that thing will be canceled. Because if this thing runs some potentially complex computations, it's not worth doing them and using a platform thread to perform all these computations, but it's worth canceling that out, which io.race does automatically. So you have this concept of racing, which automatically does cancellation. Speaking of cancellation, you can cancel effects at will in any point that you like. Let's take a look at this. So we have 3 IOs, so 3 computations that are running in sequence. One is let's say a UI that says, if you're ever paying with card, if you ask for a confirmation, you have this spinner that says, please don't close your system. I'm paying with the card right now, right? Then you have whatever transaction is being processed there, and then you have the UI saying payment completed. It has the little visa with a check mark and says, yeah, payment was completed. You're a little poorer now. And then these things are happening in a sequence. But then if you have on cancel, because programmers did think of the idea of you turning off your system while the credit card was being processed, some effect is being produced there to get the money back in your wallet or whatever. So you can cancel this thing at any point, in which case at any delimiting chain of the IO, so at this stage or at that stage, or at the payment completed, you can cancel the IO chain in any way that you see fit. Or you can turn effects or chains of effects into transactions. You can simply mark them uncancelable, and this payment system will act as a single transaction. So even if you call cancel on that, that cancel signal will not be processed. So you can mark things cancelable or uncancelable. You can turn things as transactions, and you can manipulate cancellation as you see fit and manage concurrency in that way. One very powerful construct in Cat's effect is the idea of uncancelable. So you can say io.uncancelable, and inside you can run arbitrary logic. So this is an example for authentication. You have an input password effect, a verify password effect, and a check. If the verification works successful, you'll see this UI with auth successful, otherwise you'll see auth failed. The interesting thing is that this chain can be canceled at the point where the user is about to input their password, and if it takes too long, if it takes like 1,000,000 years for them to input the password, they should be forwarded back to the home page or whatever that was. The interesting thing is that you can mark anything inside this lambda, inside this computation. This thing is uncancelable, so nobody can cancel this unless you use this little argument to unmask a particular effect and mark it cancelable. So everything is uncancelable except this. This is mega powerful because you can make an arbitrary computation and turn that into a transaction except something, or except 2 things, or except 3 things that you think should be left to be canceled. And in this case, if the input password takes too long, this thing will be canceled. So because we have potential cancellations, we have primitives for concurrency. We have ref and deferred. These are the 2 fundamental concurrency primitives in Cat's effect. One is an atomic reference, and you can build them with io.ref, and you'll get an io that's wrapping an atomic reference. And then you can flat map that, and you can modify the atomic reference with known modifiers like get and or update or retrieve and set, that sort of thing. And the other one is called deferred, which is an effectful promise. And the fundamental operation of a deferred is get, which semantically blocks the effect running on whatever light thread is running on until the signal has a value to return. And one is called complete, which is the API for another fiber to unblock whoever is waiting on that effect. So with ref plus deferred, you can build any concurrency primitive that you want, because you can produce consumer patterns, you can enable notification services without actually blocking JVM threads or platform threads at all. You also can build arbitrary concurrency primitives, the likes of which you've seen in basic computer science, so mutex or semaphores or cyclic barriers or countdown latches or anything else, or software transactional memory, by the way. You can build all of those just with ref and deferred, and you can control semantic blocking or by making effects wait in the style that you saw earlier. One very important utility in Cat's effect, which is based on this idea of programs as values, is called resource. So using a resource, we've all written software that uses and closes resources, and we are more or less careful with closure of resources. So using a resource is done in 3 steps. One is to acquire, to use, and then to close the resource, and we generally forget the 3rd step. Resource is a composable abstraction that focuses on the usage pattern, but then the acquire and release is specified at the beginning, letting you use that later in any way that you see fit. And the construct for that is resource.make, and you specify the effect that is being performed to acquire the resource, and the effect that is being performed when releasing the resource. And then later in your code, you have this construct. It says .use, and then when the effect is done, the closure happens automatically. So you specify how the resource is being acquired, how the resource is going to be released, and then later in your code, you can forget about all of that and just use the resource, and it will be released automatically. So resource has all sorts of functional programming transformers and error handlers and finalizers. These are some of the examples. So this is a composite resource that, for example, opens a file, gets a connection string, and opens a connection with the URL read from that file. And you call use on that here. And when this effect is done, all the resources get closed automatically, which frees up the mental space for us to just think our business models in terms of effects, and letting the resources deal with acquisition and release. Now, Cat's effect being Cat's effect, it brought that idea of a program as value further. So instead of doing IOs or options, which is used for testing, or even my own data structure that we saw earlier, we think generally, we call that F. This encoding is called, in an improper name, it's called tackless final, but it's more like polymorphic effects in the sense that you can specify any sort of effect. And the capabilities that I was describing earlier, like the functional programming primitives, the error handling, cancellation, the ability to spawn fibers, the ability to lift asynchronous computations to an effect, these are taken away from the specification of the effect itself, and it's being split into the type classes that describe all those capabilities. So map and flat map, that's a monad. Error handlers, it's called monad error, just map and flat map plus handle error with. Then we have cancellation, we have spawn, concurrent, async. These are type classes that abstract away the idea or the capability of, for example, spawning threads. Now you can call these respective methods, or by extension methods, if you have these type class instances in scope. And this is an example. So instead of io.uncancelable with the auth program that I talked about earlier, with the auth timeout, where you can cancel just the input password, you can abstract this away. Instead of io, you can define a little method called auth flow. You can pass any sort of effect type F. And if you have a monad cancel in scope, this is what the using clause is, it's an implicit value, then this is going to return an F unit. And you have uncancelable, so like we did earlier with io.uncancelable, MC, which is the monad cancel instance, grants you the capability of calling uncancelable with the same semantics. So this lambda is completely identical. It's just the phrasing of uncancelable effects that has changed. And this paves the way for polymorphic effects. That's just an example. Everything makes sense so far? Can I get a show of hands? All right, good, awesome. Thank you for following along. It takes me like 8 hours to talk about all this in my Cat's Effect course, so you're doing great. Awesome. So in terms of software architecture, I talked about this in another presentation that I called the type level rite of passage. The architecture of an application that uses Cat's Effect, the way that I generally think about something like this is kind of like an onion architecture with some layers segmented, or the hex architecture without a lot of ceremony with ports and adapters. And I'm going to talk about what I mean by that. So if you think of your application starting from the core, which is the domain model, on top of that you can have the repository or the core functionality. Then on top of that you have the service, which approaches the API layer. And then on top of that you have the UI, which can build like testing or consumer-facing APIs or front-facing applications and so on and so forth. So in terms of meaning, what the application does, you have a user domain, repository service, and whatever I want to log in terms of auth, or here's an API key for automatic authentication, or the test everything. You can replace that layer with something else that uses the layers below. This is the kind of way that I like to segment my own applications that are using FX systems. Or you can unwrap them and you can replace the service with a test service layer that just uses the layers below without the UI. So you can test the repos or whatever you want. In terms of hex, you have the core logic described as the business logic in terms of these 4 comprehensions or using resources and whatever. The actions or the runtime happens from the Cat's Effect runtime that schedules these effects and runs them without you having to care too much about them. And the UI submits some requests that are going to be performed later. That's the general flow of it, and you'll see the results back when those effects are being evaluated. So let me give you a real life example. This is something that I personally use in one of my projects. This is an authentication layer that uses the polymorphic effects style with this f-type parameter here. And with a bunch of methods, I just kept the login and sign up, and we have some parameters here. And you have f option user, f option user. The way that you instantiate one of these is to create a smart constructor. I called this live auth, and has an apply method that uses these things. Now, non-Scala developers, can you shake your heads or something if this thing makes sense? These things are instances of type classes that are passed implicitly. So this thing can work at the compiler, so the code will compile if you have an async type class in scope, and if you have a logger type class in scope. Otherwise, the code will not compile. And these things have, this auth live representation has some parameters. These are dependencies, so this is basically an explicit dependency injection. And this can perform an effect, so you return an F, where the value that will be returned is a live auth implementation. And then you'll allow the user to log in, whatever. So this is a real-life representation of something that uses polymorphic effects. Now, here are some pros and cons. This is another example where I'm building the core layer, that orange thing, this is for a jobs platform. This is the jobs repository, users. This is for authentication. This is for the email newsletter. This is for the user database. This is for authentication, and this is for the payment service. So I'm using Stripe to process payments, and this is the only data structure that I need that gives me access to the domain model, and I'm returning that as a resource. So resource is great. So layers will click like Legos in that style. So you have a for comprehension that makes it explicit which layer needs what. It's very easy to configure, and it's also easy to replace one of these layers. So for example, if I don't care about the email service, if I want to mock that, or if I want to not send emails, I can just replace this with like dummy emails or whatever that doesn't really perform anything and doesn't charge me a lot for MailChimp or whatever service that I'm using. And it's easy to navigate because it's clear. So it adds clarity of what these modules mean. Now, this thing requires some discipline because this thing is not really easy to read, especially for beginners or newcomers, and it takes a little while to get accustomed to this style. Errors are very much invisible unless you take some effort to surface them out or catch them early, because if something goes wrong, for example, with the tokens or whatever, you kind of have to trace that, and if you don't have good knowledge of the tools, it's pretty hard to trace them back. And it becomes tempting to misunderstand in the terms of dependency injection, because these things like live jobs, users, tokens, whatever, these are explicitly passed, but you can also pass them implicitly, just like the type classes that grant you capabilities. So you can very easily end up with something that looks like this, where all of these instances are being passed as implicit values rather than passing them explicitly. And there is a fine demarcation for which things should be passed implicitly, like capabilities, versus explicitly as dependencies. So this was Cat's effect. I'm going to talk about ZIO next, and many of these concepts that I talked about earlier in Cat's effect will be transferable to ZIOs, hopefully. So here at ZIO. Back to my effect. So my effect wraps a arbitrary lambda that takes no arguments and produces a value. Map and flat map and whatever. Now, we can think of this my effect as an arbitrary program, so this can do pretty much anything, but not really anything, because we are not tracking errors, for example, and we are not tracking dependencies. For example, that lambda could have been something that takes an argument rather than have a zero lambda. So this is not a full program because it does not include error management or dependencies in the type signature, so we need a change of that signature, and we can decide that effect to look something like this. Instead of with a single type parameter, we can call this a rich effect that takes multiple type arguments, One is called requirement, that is the argument of the lambda. And instead of producing a pure value, it can produce either an error or a value. This is a richer effect and has a more complicated signature, but it's also more powerful because multiple things are in your face now. So this is ZIO. It's a richer super effect that has these type parameters. One is called the environment or the requirements. This is the error type, and this is the value type. So if you create a ZIO that fails with nothing, this is an infallible effect. So this will never fail. You can only build that with something like ZIO succeed. A failure can be built with any exception, like on the JVM, but you can produce a failure in terms of data structures, like a string or a case class or whatever your domain model happens to be. For comprehension, so map and flat map in the same style as we did earlier. This needs no explanations or little explanations. So for this ZIO, we have the same core ideas. So we have the same FP style transformers, including error handlers like handle error with, redeem, or die, things like that. We also have the concept of a fiber or a light thread and the same concurrency primitives like ref and deferred. We also have the concept of semantic blocking because these things can block without actually blocking a platform thread or a JVM thread. We also have the concept of pinpoint cancellation and error handling. So the ZIO library also has the concept of uncancelable or uninterruptible, they call it, but it's the same concept. And we also have things that are built on top of that, like races or retries or timeouts or things like that. So in the same, so ZIO is pretty much the same abstraction as in Cat's effect, only that you have multiple types to track. All good so far? Give me a show of hands. Awesome. Right. What ZIO does differently is dependency injection, which I find particularly useful. So I'm going to spend like a couple of minutes to talk about dependency injection. So assume a standard layered application. This is a lot of code, but I'm going to walk you through it. So we have the domain, which is in case class user. This model is kind of like a newsletter service. We have a case class user, and then we have the user subscription, which is the newsletter. And this requires an email service and a user database. So this has two requirements. The email service has just one API, and the user database has another requirement, which is the connection pool. The connection pool can build a connection, and so on and so forth. So we have user subscription requires two things. This thing requires a third thing, and in order for my user subscription to build, we need all of these to build first. So the way that you would use this user subscription is to build something like that, like an object that has whatever smart constructors you have, but you have user subscription that takes an email service as a user database, and the user database takes another argument, and so on and so forth. In order to use it, so you need to build that before you can use it. So you can, if you want to subscribe a user to your newsletter, you need to have access to the subscription service and then be able to call that API to subscribe the user. Why not assume the existence of the service, use it as if it exists, but then supply it later? So instead, assume that the required object exists and then use it later. So instead of requiring a user subscription, I'm going to use this construct, which is called ZIO.service. So if there is a user subscription in scope, then I can subscribe the user. But then if you take a look at the signature of this method, this returns an effect that in order for it to run, it requires, so this is the requirement thing, it requires an instance of user subscription. Without it, the ZIO does not run. So I can very easily focus on my business logic as if that service exists, but then at the end of the world in my program, I need to supply that instance of user subscription so that I can run it. So I will provide it later. But how on earth do we provide it? I'm going to show you how. ZIO has the concept of layers. So these are effects that will be run when the value that a ZIO requires needs these layers to be performed. So in this case, for user subscription, I will create a companion object that returns a little effect, that instead of ZIO, it's called ZLayer, that in order for it to run, it requires an email service and a user database. And if these things exist, I will produce a user subscription with these two pass-as arguments. For every service that I'm going to use, I'm going to produce one of these layers that given whatever the requirements they have, I'm going to produce an instance of that. So, in other words, the connection pool is a layer that just builds connection pool. The user database assumes a connection pool, and if so, produces a user database. And then finally, the user subscription assumes these two, and if so, I'm going to build one of those. So, if we have something like that, this is pretty much to take in. I do understand it. But it's like implicit values in the sense that you can use the layers at the end of your program, and the ZIO runtime will take care to instantiate those effects and return the results and pass them to the ZIO effects to be produced. So in other words, my program is my entire application with the business logic and whatever, and I can focus on my business logic as if nothing happens and as if my requirements are being met. And then I'm just going to call .provide, and I'm going to pass all these layers that will instantiate them before the program runs. In this sense, I can focus my mind on whatever my application is doing and then leave the requirements at the end of the world. And this frees up my mental burden because in a real application, you won't get like 3 layers. You'll get like 20 or 30 or multiple dozen. And the graph is being processed automatically, and you don't have to pass them manually yourself. You don't need to track which service requires which dependency. That thing will take care of itself. This is a real-life application. So this is a company review site in the style of Glassdoor. And you have companies and you have reviews from users. So I have a program that has a for comprehension. We have a ZIO log Rock the JVM bootstrapping, or an ASCII art of your choice. Then you have run migrations, which is my little database for Flyway. And then I'm starting the server with the API and whatever. This thing is a giant program. It has like many dependencies, all of which are being passed here. So I'm going to say program.provide, and I have all my requirements. So for example, a company service, reviews for users, my user management, web tokens, email sending, invites, payment service. Again, I'm using Stripe. This is also using an AI agent that summarizes reviews. I'm going to use one of those that I made myself, plus Flyway to run the migrations. And these things have their own requirements, which I'm passing down, and so on and so forth. So you can pass all your layers at the end of the world, and the graph will take care of itself. That's the idea. So the layers will click automatically without you having to care about them, and it's very easy to delegate responsibility to every one of these layers, and it's very easy to configure selectively. It's also easy to replace them with testing versions of them, and so on and so forth. However, error management also requires some discipline because just as in the case of Cat's effect, they are hard to trace. And if some effect has, I don't know, 10,000 stack traces and stuff, it's very hard to trace them across fibers. And any non-trivial implementation can push type inference to its limits because if you have many different requirements that requirement type in the type signature, for example, where was that? I think it was the user service life that had emails, invites, and the Flyway service as dependencies, if I remember correctly. Type inference in Scala can push the compile time quite heavily. So these are some of the pros and cons of ZIO. I'm going to talk briefly about Kio. This is a third major effect system in Scala that is just popping up and is going to turn 1.0, with a disclaimer that I don't have that much experience with Kio besides like school grade level code. So I'm just going to talk about some basic principles. But Kio is proving to be pretty promising because it's a different phrasing of what an effect is. So instead of I/O that we saw in Cat's effect and in ZIO, we have this little thing which is called pending. In Scala, by the way, we can use non-alphanumeric names for things, which also can be used infix. For example, you can say int less than any. It's called in pending any. This is a description of an effect that will produce an int, provided that it requires this thing to be run. For example, if you want to describe an effect that runs synchronously, you can say sync.defer, so you have smart constructors passed everywhere. You have sync.defer, and this returns an effect that produces a string given the presence of a sync requirement. They call it an effect. So this is a different phrasing of the same idea, because the Uber effect is this. This is the data structure that will be scheduled, and it will be supports all the concurrency aspects and so on and so forth. And all the functionalities of cancellation or light threads or whatever, instead of passing them to type classes, as in the case of Cats effect, you have actual data structures that are called sync or async or abort or loop. There are like several dozen that are supported in Kio. So each functionality is given by one of these data structures. The good side of Kio is that the structure of the effect also allows direct style Scala that I'm going to talk about later. If you want to compose effects, you can compose constructors like sync.defer, and you say abort.get. This is potentially an effect that may fail. And this thing is an effect because it answers yes to all the three questions. So the type does describe an arbitrary computation. The value that will be returned is the first thing that is being mentioned in the type signature. And in case of side effects, the description and the execution of the effects are separate. Some pros and cons. We have the same familiar ideas of programs as values and whatever. It has some increased clarity because in the type signature of an effect, you have the description of what is required for that effect to be produced. It also allows direct style Scala without the maps and flat maps, so without any complicated transformers. And it can also interoperate with Cats effect and ZIO. Each requirement, however, has its own rules and its own constructors, so they're not necessarily a standard for how to build your own effects, and you need to conform to all the rules. And the type inference is very, very quickly pushed to its very limit in Scala. And the Kio team, I think there were a number of times when the Kio team requested some features of the Scala compiler just to unblock them for type inference. So this was Cats effect, ZIO, and Kio. Why effect systems? I'm only going to take just a couple of minutes. Why do we need effect systems? I'm going to talk about why to effect and why not to effect. This idea of programs as values enables us functional programmers to deal with arbitrary software and conform to the same principles to map and flat map and transform and pass things around and return them as results without changing the significance of the code or to lose trust in the code. So it adds clarity by the type system with capabilities, with error handling, with programs as values. It also makes testing and refactoring much easier because you can swap some effects with other effects that only do limited things. And it offers principal concurrency because you can use Cats effect or ZIO or Kio in Scala.js, for example, or in Scala native that does not have the luxury of JVM or multi-core computations or multi-threaded in this case, in the sense of JavaScript, but the same ideas will be true and will be usable on those platforms as well. Performance is unaffected in the sense that you may think that creating all these data structures can impair performance, but we are functional programmers. We know how to pitch these to non-functional programmers, right? So we can write very performant code without the loss of generality. Also, the light thread schedulers are top-notch, especially in the more mature effect systems like Cats effect and ZIO, sometimes surpassing even the native schedulers like Project Loom with virtual threads. Effects are best used for important software, so for authentication, for banking, for things where consequences are severe. And if you have an experienced team of software engineers that knows this stuff, you can build very powerful software very quickly. And this is the pitch of Scala that I always tell to people. So the main benefits are increased safety and trust in your software with the high dev velocity if those requirements are met. Why not to effect? Well, this idea of programs as values with the complex type signatures and so on and so forth, it takes a little while to learn. And it takes a while to internalize that discipline. So it requires deep comfort with functional programming, and I'm sure that this is a big green check mark here for the people in this room. And it needs some experience to use successfully, because you can shoot yourself in the foot if you're not careful. And this is the worst for, and where this is not advisable to use for software where consequences are not so severe, so things that are just lightweight in nature, or if you have an inexperienced team, or if there is a need for speed. So a combination of low stakes plus a need for speed, plus if you know another stack well, it's okay to not use an effect system. If you use an effect system poorly, so if that requirement is not met, you can very easily get into unreadable code and trash that altogether and write it in something else. So this is an overview of effect systems and whether or not you should use them. This was my presentation. This is my website, Rock the JVM, where I teach pretty much everything in the Scala ecosystem. I leave it here for posterity. If you have any questions or if you want to talk more about effect systems, I'm happy to join the conversation after the talk. Thank you so much.
Yes, thank you, Daniel. Just going to ask, before we let you off the stage, do we have any questions in the audience? I see Magnus is ready with the mic. Okay. Giacomo, yes, yes.
Thank you. So you were talking briefly about Project Loom, and
Yes.
with all these projects, since they're giving their own abstraction of forks, joining, and fibers, can they allow to transparently adopt Project Loom under the hood as an implementation detail, instead of doing their own thing?
Yes.
Can they do that?
Yeah. I mean, they are fundamentally compatible with Project Loom. So instead of using their own thread pool and whatever, they can use virtual threads instead. But it doesn't change the semantics of the code. So the semantics is unchanged.
Okay, any more questions? Don't be shy now. Okay.
Don't be afraid of the AI killing us all, though.
Okay, yes.
I have a
question over here.
So if people are not asking direct questions about the presentation, maybe I can ask you just a suggestion how to pitch functional programming to non-Scala developers, because it's for you it's easy, but for me, for example, sometimes it's really hard. They say why don't you just use Python or something, and it's how to in a simple way pitch people the idea of this.
So the way that I explain Scala to people is, so I went to a bunch of Java user groups and things, and they asked me that exact same question, why on earth you should use Scala? And the phrase that I always seemed to pop out of my mouth was that, at least for me, Scala allows me to write very powerful software very safely and very quickly. That package is very, very hard to achieve. You have to kind of pick two, either speed or safety or reliability. So if you can build software quickly, it might not necessarily be safe. If it's quick and safe, it might not be convenient. If it's convenient and safe, it might not be quick, and so on and so forth. Scala allows you to pick all three. So Scala is a great mix of speed, so productivity, safety, and convenience. This is the kind of pitch that I would give them. And if they don't trust me, that is perfectly fine. If they have their own preferred way of doing things, because if you know your stack well, you can write there are guys making millions of dollars a year on PHP, right? It's okay for them to have their own stack, but Scala for me is this great mix of speed, safety, and convenience. That's the pitch. Thank you. We have another question in the back.
I'm very new to Scala, but can you use cats, Kio, and ZIO together, or do you have to choose one, or is it overkill?
There are instances where it might be advisable to interoperate, but generally people do choose one stack. There are interop libraries between these three. especially towards Cat's effect. So Cat's effect is the stuff, and there is a ZIO to Cat's effect, there's a Kio to Cat's effect, interoperable library, and so you can interoperate, but generally not.
Thank you.
Going once.
Yeah. Any more questions?
All right.
Oh wow! Now they're popping up all over. Oh, sorry. Okay, we got the one in the back first. Let the mic just walk around. Sorry.
I guess this is more about Scala specifically. In my experience, what makes Java and especially PHP bad in more of a so-called enterprise setting is that the complexity of maintaining code increases faster than the code size.
Yep.
That's the thing I like with functional programming, that it makes the code more manageable for a big code base. But now, for my untrained eyes, you seem to introduce some more or less object-oriented concepts with these effects that looked very familiar to injects in Java, which was one thing for me that made Java very unwieldy in big projects. So I guess my question is your experience when using this for big projects, if it aided the bulkiness, maintaining the bulkiness of the code, or it easily became detrimental?
It was never detrimental for me. The dependency injection and stuff is managed as you saw in different styles. So in Cat's effect, it's explicit. In ZIO, you can pass them all at once. That never was a bottleneck for me. I mean, in things like Spring, you have to kind of keep a mental track of which feeds into what. But here, it was never a mental burden for me. So the mental burden was never increased as a result of branching out complexity. It was never that for me. Your mileage may vary, so I cannot speak for everybody, but it seems to me that they keep productivity without bringing in a lot of OOP bulkiness and boilerplate into the picture. Did that answer the question? Okay, thank you. Okay. All right, going once. Going twice. Thank you, guys. Thank you so much for coming.
Yes, and thank you, Daniel.
Thank you.